Hi, and welcome to part 2 of my attempts to build a processor from scratch. Okay, here's the clock circuit I built in the first part, and here's an empty breadboard. So this is that block diagram I wrote out, and what I'd like to make a start on today is the 16-bit address registers. Now I've been thinking about what addressing registers we actually need. The 16-bit address registers should be anything that we're going to use to access the entire scope of memory, which is going to be up to 64 kilobytes. So obviously we're going to want a program counter. It'd be nice to have a stack pointer as well, and I've written enough assembly language to know that having a couple of more general purpose indexing registers is handy. So I'm going to call these source index and destination index. This is the same name as they have on the original x86 assembly language, but if it's not broke, I don't see any reason to change it. Now, the reason why you want a source and a destination one is you might be copying between two locations in memory, or an awful lot of algorithms you might implement will be operating on two chunks of data, so being able to point at them independently without register swapping is handy. Now, I didn't mention this before, but I'm not actually planning to build all of this on breadboards. What I'm going to do is assemble the circuits and test them on breadboard, and once I'm happy with each of the discrete sections, I'll translate them onto a more permanent circuit, and I'm hoping that I might end up with something that's reasonably reliable by going down that route. Do I need more than 4? Well, I've been thinking about some of the later stages of the development, and I'd like to support function calling. And there's a couple of different ways you can do that, using either a stack, or you can also have a return address register. And I'm going to do function calls that way. I'll explain why when we get to that part. It's quite an interesting problem, actually. But I think that's the main 16-bit registers that we need, excluding the transfer register. Now, with my plans to transfer these onto circuit boards, I'm not hoping to design up a PCB, get somebody professional to make it, and then I'll solder up the components. So it's a benefit to me to make these all the same. So if we think about what we need to do for these, the program counter, I'd like to be able to increment it. Stack pointer, we would definitely want to be able to both increment and decrement it. Return address, we don't really have any particular needs, but the source and destination indexes is pretty much the same as a stack pointer, really. It would be handy to be able to increment and decrement those. So what we're after is a register with an inbuilt ability to increment and decrement, because remember, our ALU is 8 bits, these address registers are 16 bits, and we're not going to be able to shift them into the ALU, perform an increment or a decrement, and then get them back out again without expending quite a few cycles shuffling them to and from the transfer register. So I was looking around at the available chips. I found this one. This is the 74LS193 binary up-down counter. Now, this data sheet also covers the 192, which is a BCD version, which I'm not looking at here. So if we look at the functionality it's got, it goes up to 40 megahertz. Sounds pretty handy. It's synchronous. We've got a master reset and a parallel load, so we can load a value directly into its internal latches via these P0 to P3 pins, and we can read out the current state with Q0 to Q3, and it also has the count up and down inputs with the equivalent carry ones that you can directly chain them on. So this will handle 4 bits, and we'll need 4 of these to implement a 16-bit register, or at least a counting portion of the register. So I managed to get a few of these. Let's just worry about one of them for now. So we've got VCC in on the top left pin and ground on the bottom right pin. Now we need to start looking at these other pins and see what they do. Let's get some LEDs hooked up to the outputs. I've got these SIL resistor arrays, which are hopefully going to be quite handy to wire up more LEDs. So these have a common pin, which I believe is the left-hand pin here, and then these have 8 resistors all wired up back to that common. So if I put that in there, so I should be able to put 8 LEDs in here and not worrying about anything else. I've got one chip for a 4-bit counter initially, so let's just get 4 in and have a play. Get some power over here. Right, that's good. So we've got this asynchronous master reset. So that is an active high input, so I don't think we need to particularly do anything with that straight away. We could connect it over to our reset signal over here, but let's just see what it does without it. We also have asynchronous parallel load. Now that's an active low pin, so we're going to want to bring that high. So that's pin 11 here. Let's come up here. So if we bring that high, that should be okay. And now we need to bring our 4 outputs over to the LEDs. So this is Q0. Bring them down a bit. It's slightly weird on here in that Q0 and Q1 are the opposite way round than the other pins. I assume there is some logic to the internals that would that makes that appropriate. One thing I do like about these chips is the count up and the up, down and carry up, carry down are on opposite sides. So on a circuit board it would make a lot of sense to rotate these chips by 90 degrees, and then you could put 4 of them in a row and just have the carries going straight across. Okay, I've misaligned those. Obviously we wouldn't necessarily use the clock as an input to one of these. Okay, why is that not doing anything? Ah, of course. The master reset is active high, but as a TTL chip, the chip has internal pull-up resistors, so this so any pin that we don't connect is going to naturally float high up towards the 5-volt rail. So this chip is constantly being reset at the moment. So master reset is pin 14 here. Let's pull that low, and we have binary counting. Let's go. Okay, so if I just disconnect this line, the reset should go high on its own, and we go straight back to 0. And for the same reason, if I were to take this parallel load and take it and just take it low, all of those inputs are being pulled high, so it will read all ones into it and then clock it once and it goes back to 0. Right, so that gives us the ability to count from 0 to 15. Let's see if we can go a bit higher. Spent a while bending these wires to match the requirements here. So we've connected the count up carry line through to the carry in. Let's do the same for the count down. Okay, these wires are starting to get quite tight. I may have misunderestimated this. I have to dig out some longer wires in a minute. These ones get a little easier because they come back on themselves. I've actually ordered some of the dip LED arrays, but they haven't arrived yet, which is going to make setting up banks of LEDs to show registers an awful lot easier. So even these small 3mm LEDs are slightly wider than the pins on, or the pinholes on the breadboard, so they get quite troubling. Always, lean out slightly. Okay, that's not actually working because we need to get our reset and the load lines across. Power. Okay, that's pretty cool. Now it's worth looking at the other mode of operation here. Let's shift our clock line here to downward counting, and yes, that's definitely counting down. Now, one of the things I'm very interested to work out here is what the behavior is of up and down. Now, the datasheet lists these count up and count down lines as active high. It counts on the rising edge. So what I actually expected was that the ones I wasn't using, I would be tying down to the ground. Now, when I click here, this is completely bypassing the least significant bit, and it's giving me some odd behavior. If I swap these over, this least significant bit is always on, and it's effectively counting correctly from the next bit. Now, on the data sheet, there was a table of expected line use, which always has the other line, whether or not you're using the count up or count down, the other one wants to be high, which is a little bit counterintuitive to me. But if you look at the outputs from the remaining of the count carry points, they are in fact high like this. Now, I don't know why they've designed it like that. Get a couple of green LEDs for this. Just going to put these LEDs in here temporarily, just so I can demonstrate what's going on. the carry up and the borrow line. So these are high all the time. So this is the carry and borrow coming out this first chip. So this is controlling what's happening across between this fourth LED from the right and the fifth one. So once I get to a point where the next clock is going to be carrying over, the LED goes down, and then when I on the rising edge, the carry happens. So effectively it's kind of like preempting the fact that it's going to have to carry, and then it carries. So we see the carry or the borrow change for 1/2 a cycle. I'm not sure why they've done it that way, but we can certainly work with that. It does mean that I'll have to tweak the circuits a little bit from how I originally planned them, because we want those lines to remain high all the time, apart from the point before we want to increment or decrement. We bring the line low. So we just have to tweak the logic slightly. But if we carry on this all the way up here, we'll end up with a borrow and a carry which come out the full range. And I am curious to know whether or not we can find a use for that. Oh, don't want that low. This is counting down, and as this area of the register gets to 0, then the line changes. So that's kind of curious. We could use that as a zero detection. Does give me the idea that if we're kind of making a bunch of these on a production line, my plans for this register stack on for the address registers would allow for 8 indexes on this bus. So we've got the transfer register, and it might be worth adding a count register, which would be not really used as an address register at all, but having something where we could easily and quickly count to or downwards from a number greater than 255 might be handy. So stick a pin in that, it might be an idea. Okay, now I'm going to switch back and populate the rest of these 16 lines, so we've got the full range of counting, but I'm probably going to fast forward that or something, so I won't talk. It's effectively a replication of what we've seen already. Okay, so here's all the 16 bits working. So if I issue the load, all of these bits go immediately high. Obviously, if all the bits are high, then and then we clock it upward once, everything's going to go back to 0. So I just want to double check that the parallel load works as I expect. So let's just grab a couple of these parallel load pins here. So this is bits 2 and 3 of the second nibble here. So that's going to be these 2 LEDs here. So if I pull them low, now if I do a parallel load, I should see all the LEDs on apart from these 2. Yeah, that's good. Okay, so if we had all of these 16 inputs onto a bus, we could stick a value on there, momentarily drop this line low and load that value into here. So in the next stage, I will be looking at the ways of getting the values from here back out and onto the bus, and perhaps some of the more interesting timing considerations about that. But that's more than enough. All right, thanks for watching.